Dear folks, welcome to your security newsroom. Dear folks, today we will discuss about direct energy weapons. These are going to be the weapons of the future. Direct energy weapons or DEWs are advanced systems that use concentrated energy, for example lasers or microwaves or even particle beams to disable or destroy targets. Unlike conventional weapons used, like the bullets or missiles, these DEWs deliver energy at the speed of light with no physical projectile involved. Now, let's discuss its types and how it works and also the materials involved, the engineering principles operating behind them. DEWs can be categorized in three main types, each with unique physics and applications. First is laser-based DEWs. The principle it involves amplifying light into a focused beam to burn or melt targets. A laser generates coherent light, all waves aligned, using what can be termed as a lacing medium. For example, crystals, gases, or fiber optics. Powerful energy source like electricity or chemical reactions excites the medium's atoms, causing them to emit photons. Mirrors reflect these photons back and forth, amplifying them into a powerful beam. A lens or mirror focuses the beam onto a target, transferring intense heat up to millions of watts. A high-energy laser can burn through a drone's hull in seconds. Before discussing the concept, let's have a brief overview of countries who are developing these direct energy weapons. As of today's open source information, USA is leading DEW's project with building a laser-based energy weapon that can generate 300 kilowatt of laser. US Navy is developing the laser weapon system, or known as LAWS, and also Helios, which means high-energy laser with integrated optical dazzler and surveillance. US Army is working on indirect fire protection capability high-energy laser, IFPC HEL. U.S. Air Force is working tactical high-power operational responder known as Thor for counter-drone systems. The U.S. military is also working on high-power microwave, HPM, systems for electronic warfare. Whereas LW-30 is a Chinese laser defense system designed to intercept drones and other targets. China is also exploring space-based DEWs for potential anti-satellite applications. Reports also suggest China is developing HPM systems for use against electronics and drones. On the other hand, Russia's Peresvet is a laser system reportedly deployed for air defense and anti-satellite purposes. Whereas Zadira is Russian laser system claimed to be capable of destroying drones and other targets. Russia is also working on radio frequency weapons for electronic warfare. British Dragonfire is a high-energy laser system being developed for the Royal Navy to counter drones and missiles. Israel's Iron Beam is a laser-based system designed to complement the Iron Dome missile defense system. HELM-P is a French laser system designed to counter drones. France is also exploring DEWs for space applications. Durga 2 is an Indian-directed energy weapon program focused on laser technology. Iran has also claims to have made advancement in laser-based weapons. Second is microwave DEWs. It emits high-power microwaves to overload electronics of the gadgets. A magnetron or klystron, vacuum tubes, generates microwaves including radio waves ranging from 1 to 300 GHz. An antenna directs the microwaves into a tight beam towards target. The waves induce currents in electronic circuits, frying components like transistors or capacitors. For example, a vehicle's engine control unit, ECU, could be disabled by a microwave burst. Third type is particle beam DEWs. It fire accelerated charged particles, electrons or ions, to disrupt the matter. Particles are accelerated to near light speed using electric fields, like in particle accelerators. The beam ionizes atoms in the target, causing structural damage or radiation. For example, a particle beam could penetrate armor by breaking molecular bonds. Now let's discuss materials used in DEWs. These require specialized materials to handle challenge of powerful current production. In dealing with extreme energy levels, heat and stress, laser components lacing requires a particular lacing medium to operate accordingly. For solid-state lasers, synthetic crystals, for example neodymium-doped yttrium, aluminum garnet, or fiber optics. For chemical lasers, reactive gases, for example hydrogen fluoride, that release energy via combustion is required. Free electron lasers uses electrons accelerated through magnetic fields. Other material include mirrors or optics, coated with reflective materials, for example gold or silver, to handle intense light without melting. Lenses made of fused silica or diamond are used for heat resistance. Original challenge is to develop better laser system that can increase the impact distance of laser range. The challenge is making portable high electric power generator which is needed to narrow a beam at a remote site. Other major issue is the cooling for material handling. Copper or aluminum heat sinks are often used to dissipate waste heat. Liquid coolants, for example water or ethylene glycol, circulate through channels or used to keep system heat resistant. For microwave wave generators, components include magnetrons used in microwave ovens or advanced gyrotrons for higher power. It must be made of copper cavities and ceramic insulators to reduce heat. Some antennas are also rewired. Parabolic reflectors, aluminum, to focus microwaves in a particular direction. For particle beam components, first one is the electron accelerators. Superconducting magnets including niobium titanium alloys to steer particles. Vacuum chambers, stainless steel, to prevent particle collisions with air molecules. Power supplies require heavy load capacitors and transformers to generate high voltage pulses. Now let's talk engineering behind DEWs. The direct energy weapons integrate multiple engineering disciplines to function reliably. A chemical engineering is the first aspect. A science of coolant fluids is required to immune system from overheating itself. Chemical engineers design non-conductive high heat capacity coolants, for example fluorocarbon fluids, to prevent electrical shorts. Some chemical lasers require fuel combustion, for example hydrogen plus fluorine excited hydrogen fluoride gas provides energy for the laser. Engineers optimize reaction efficiency and safety. Thermal management is needed to get heat exchangers and phase change materials, for example paraffin wax, absorb excess heat at component terminals. Other aspect is of mechanical engineering and structural design. DEWs use lightweight alloys, titanium carbon composites, to withstand vibrations and thermal expansion. For beam steering gimbals and servo motors adjust mirrors, antennas to track moving targets. Internal cooling systems uses pumps, radiators and heat pipes to maintain optimal operating temperatures. For electrical engineering and power generation we require capacitors, batteries, for example lithium-ion, or explosive-driven generators for pulsed power, supply massive energy bursts. For beam control loops adjust beam focus using adaptive optics or deformable mirrors. For pulse modulation high-speed switches, thyristors, shape microwave or laser pulses for precision is required. Now finally discuss challenges and limitations. Power requirements of any DEWs need enormous energy. For example, a 100 kilowatt power laser requires 300 kilowatt of input power. Atmospheric distortion including thunder or lightning and also humidity, dust or wind can scatter beams reducing effectiveness. Heat management, even small inefficiencies generate destructive waste heat. Ethical concerns include DEWs could enable invisible warfare with less accountability. About the future of DEWs. Miniaturization, portable lasers for infantry or drones. Hybrid systems combining lasers and microwaves for multi-target engagement. Space-based DEWs include orbital systems for missile defense, but with no atmospheric interference. One can say in conclusion that DEWs represent the cutting edge of military technology, blending physics, chemistry and engineering together. While still evolving, their potential for precision and reduced collateral damage makes them a transformative tool. If ethical and technical hurdles are addressed, understanding their workings demystifies their role in modern warfare and highlights the interdisciplinary innovation driving their development. For more such videos, please subscribe, like and share.